Hello, and welcome to the IEEE Computer Society's presentation on simulations that can save lives, part of the Best Paper webinar series. The webinar will be presented by Sebastian Ullrich, co-author of the paper Haptic Palpation for Medical Simulation in Virtual Environments, which was awarded the Best Paper at the IEEE Virtual Reality 2012 Conference. My name is Dante David, and I am the Program Manager for the Best Paper webinar series at the IEEE Computer Society, and I will be moderating the presentation today. Before we get started, I would like to mention some housekeeping items. You can control the volume of this webinar by adjusting the master volume on your computer. At the end of the presentation, we will have time for some questions. Please type your questions in the question box and submit them. If you do not see the box open, please click on the orange box with the arrow to view it. You may type your questions anytime during the presentation. Now I would like to introduce you to our distinguished presenter for today's webinar, Dr. Sebastian Ullrich. Dr. Ullrich is a research and development specialist for medical simulation. He currently works for SenseGraphics AB. He holds MS and PhD degrees in computer science from RWTH Aachen University. From 2007 to 2008, he was a visiting research scholar at the National Institute of Informatics in Tokyo, Japan. His research interests are primarily in the areas of virtual reality and medical simulation, with a special focus on soft body physics, simulation, and haptic rendering. Since 2008, he has been a member of the Web3D Consortium and an integral part of the Medical Working Group. We are delighted to have with us today Dr. Sebastian Ullrich.
Thank you very much for the introduction, and also from my side, everybody welcome to this webinar. And now I want to begin with the presentation. So this talk will be divided into two parts. First, I will give a presentation which I've also shown at the conference, and afterwards I will have some bonus slides. So let's get started. The first part of the talk is divided into several sections. First, I give a short motivation and introduction on the medical and technical background. Then I will present a palpation interaction approach, which was one of the main contributions of the paper. And also I will present the results of a medical user study, and then conclude this part of the talk. After that, continue with some bonus slides. So first, the motivation. For the training of medical procedures, there's different ways of doing this, and very often is still an apprenticeship approach where the new doctor observes the procedure, then rehearses, and then also distributes his knowledge. And there's different ways, like mannequins can be used, or training is done on animals or corpses, and also on real patients, which bears certain risks. So one alternative is to use a virtual reality-based medical training. However, there are many challenges in the development of such simulators. For example, we need to have a physics-based simulation for deformation of soft tissue, for example, and we need to provide visual and haptic feedback, and everything has to be performed in real time so that the interaction is fluid. And also all these components need to be evaluated together with medical experts. And yeah, in this talk I will focus on palpation simulation. And for this I will first explain what is palpation. the palpation is a physical examination technique that's used in all kinds of medical procedures. And for example, it's used to locate anatomical landmarks such as bones or blood vessels. And there's also some related work, but I don't want to go into detail about this. Other approaches that simulate palpation. Just to summarize, most of them either focus on haptic rendering or they focus on physics-based deformation, and these two components are seldomly combined. So this is one of the differences in this approach. And furthermore, pulse simulation has not been documented in this related work. And for this we also give an algorithm. So for those of you who are new to this field, I've also included some introductory slides on haptic input devices. So here's an example of such a device which is commercially available, the Phantom Omni. And this device can be used as an input device with 6 degrees of freedom. So the stylus can be moved in space, and the position and the orientation are read. And also the device can be used for output, so to give out a force. And a 3-dimensional force vector can be put out with this device. And what's also very important, in order to get a good haptic sensation, the haptic rendering has to be updated at 500 Hertz to 1 kilohertz, because otherwise if this threshold is not reached, then vibrations would be felt, which destroy the illusion of the haptic render. So this concludes the background. Now I will come to the contributions of this talk, the palpation interaction. And for this I first give a short overview. So we need virtual representation for the user. In other works, this is sometimes done just by some point or by some kind of pick ray. And we, however, use a virtual hand model, and we extended 2 fingers, which can be used to probe the virtual scene. And then we have to define some interaction behavior for this virtual hand. For example, we want to prevent it from penetrating a virtual patient. Also, it should be able to deform and drag soft tissue, and we want to be able to feel structures that are beneath the surface, and the pulse should be possible to feel. And the hardware, so we are using a haptic device, just as I've shown before, and this should be also modified to provide a more natural interface for the palpation task. So first, how do we couple the haptics device to the virtual hand? We use the center point of the haptics device and map this to the fingertip of the probing hand. And then also we use a collision ray, which we align with the stylus of the haptic device, and which is also aligned with the extended finger of the hand. And then when this collision ray is penetrating an object in the virtual scene, we constrain the virtual hand to the contact point so that it doesn't intersect the virtual patient, for example. So the next task is, how do we achieve what you can see in this video? So how do we achieve that the virtual hand can drag some simulated soft tissue. And for this, we use a stick slip friction model with, for example, Carnot friction. And then, depending on the friction state, we can create external forces that are sent to soft tissue simulation and thereby deforms the soft tissue. So for this, I will now present an algorithm. So in the first step, we save a contact point when the virtual hand is colliding on a surface. Then we are searching for the nearest node in a behavior mesh. And this behavior mesh is a representation of the soft tissue in a soft tissue simulation, which can be, for example, finite element-based simulation. And then we compute a force vector in the normal direction. And we also compute a force vector in lateral direction from our initial contact point to the current point. And this lateral force is either 0 in the case that the normal force is below a stick threshold, which is basically a friction coefficient. And if the normal force is above this threshold, then this lateral force is applied and thereby the skin is dragged. And so we summarize these two forces, the force in normal direction and in lateral direction, and apply it to the behavior node. And we loop through this for as long as either the friction constraint is fulfilled, so the normal force is high enough. And we also check when we stretch laterally that we are below a certain strain threshold. So for example, after a few centimeters, we would not be able to stretch the skin anymore. It would slip back under our finger. So this concludes the description of an algorithm to perform the tissue dragging. And now I want to focus on the force feedback for the palpation. So the haptic cubes are very important for palpation in the real procedure. And so we came up with some requirements which we got in collaboration with medical experts. So the sense of touch of the surfaces should be replicated. Also objects that are below the surface should be simulated, and the pulse should be simulated. And in order to do this, we are using an existing approach and extend this to subsurface structures. And we create a new algorithm to simulate the pulse. And so first of all, in order to simulate touching a surface, we use a well-established approach based on constraint planes. And so what you can see here in the picture, when the input device is penetrating the surface, a constraint plane is computed. So this plane is going through the contact point and defined by the contact normal. And this constraint plane is then used by a force rendering algorithm. And as long as the input device is below this constraint plane, a force is computed to that tries to push back the input device to the constraint plane. And then for objects objects that are below the surface, we simply extend this approach. So we create additional constraint planes, and then we also align those planes to the outermost plane, and thereby we have we can simulate multiple objects. So now for the pulse simulation, we first look at a pulse signal, and so in reality this can be very complex, and here we just approximate the pulse signal by a rectangular function, and then we still have the problem, when do we want to render the pulse? So here I'm showing an example of the artery that's going through the upper leg. This is already a simplified artery. Usually it's branching off even more. And for the haptic rendering, we need to maintain an update rate of up to 1 kilohertz. And so our collision detection approach, distance estimation approach must be very fast. So naive approach would be too complex for this. So what we propose is to use some point sources for pulse. So the pulse center PI, we can compute the distance of the input device to this pulse center, and then depending on the rectangular function, this force is either 0 or it depends on the distance between the pulse point PI and the position of the input device. And furthermore, we have a radius of influence. So if our input device is outside this radius, then we cannot feel a pulse at all, and the closer we get to the center, the stronger we feel the pulse. And so with this simple approach, we can discretize an artery by defining multiple pulse points, and then we can also embed these pulse points very easily, for example, in our soft tissue simulation, so that when the soft tissue is getting deformed, we transform the pulse points accordingly, so that the location of the pulse can be dynamically shifted during palpation depending on the pressure and so on. So this concludes software contributions of this approach, and now I come to the to a hardware extension. So we are using this phantom-only device, and the default interface of this device has a stylus, but the stylus is being held like a pen, which is not very intuitive for palpation, and so the requirement is to have a different grip for palpation, and also this alternative extension should be lightweight. For example, this pen can be removed, and this pen only weighs 25 grams. So if you would do something which is heavier, then the maximum amount of force that we could output would be reduced. And yeah, we want to keep the weight down as much as possible. And also we wanted to create something which is easy to construct, so that also other researchers could reproduce it easily. So we've created several prototypes in close collaboration with medical experts. And so here you can see the result of this. This is a palpation pad. You can see that the finger posture is like in a palpation procedure, and this palpation pad is constructed from acrylic glass, which has been cut with a laser cutter, and it's connected with a jack plug to the haptics device, and the surface of the palpation pad has been glued some rubber foam on it, which has some neutral surface properties, and we also use some rubber band to strap the fingertips to the palpation pad. And so this concludes the palpation interaction approach, and now I come to the medical user study. And we've performed a between subject design and recruited users with different level of palpation expertise. And the task was to locate femoral artery by palpation. So this is the artery in the upper leg. And additional task was to perform a femoral block on the virtual patient. This task was only done by medical experts. And as metrics, we observed the test subjects, we interviewed them, and we used questionnaires. And the goal of the user studies was to evaluate face validity. So face validity is a measure to see how closely the simulator can resemble the real procedure. And construct validity is a measure how good a simulator can differentiate between different levels of expertise. So our hardware setup for the user study was two kinds of setups. So one was a mobile setup, which we also used at conferences based on a laptop. And the other system was a semi-immersive system with a rear projected screen, and the user was wearing stereo glasses, and furthermore this was head tracked, and so the test subject was standing in front of the screen and looking down on a life-sized patient. And in both cases, we used two haptics devices for input. One was used for the palpation, the other was used for needle steering. And so the software scenario that we used was femoral block from regional anesthesia. So in this procedure, the doctor has to rely heavily on palpation before he inserts the needle. And the system has been realized with a bimanual system architecture, which I have described in another paper in more detail. And for interaction, we support on the one hand palpation, and on the other hand the needle steering and insertion. And from the simulation side, we are using finite element-based soft tissue deformation. We used a software toolkit called SOFA for this, and then we've also had our haptic rendering and so on, which I've described before in the palpation interaction approach in detail. And for the visualization, we had our virtual patient and instruments, so the palpation hand and the hand with the needle, and we've also added virtual shadows to the scene in order to improve depth perception. And in the lower picture you can see an anatomical view. So there it's possible to look inside of the patient in order to check if the needle insertion was successful or not. So our participants were recruited at different venues and were grouped by level of expertise. So our first group was a non-medical group with simulations experts that we recruited at a medical simulation conference last year. And then we had some anesthesiologists which had up to 5 years of work experience, and then we had anesthesiologists with more than 5 years of work experience, and we had some more anesthesiologists that participated in a medical workshop, and which we also recruited for this user study. And so this slide shows just a brief excerpt of the extensive questionnaires, and this compares several data from the different groups. And in general, the system has been rated best by the non-medical group, so they don't really have that much real palpation experience, so they are easily to convince of the simulation. On the other hand, the experts group rated the pulse simulation best among the medical groups. So this could be an indicator for construct validity, that the system distinguishes between different levels of expertise. And also the palpation pad has been rated positively by all medical groups. And on the next slide I will show some more about the palpation pad. So we compared the pad against the stylus. So we asked the users to do their task with the pad and then repeat the task with the stylus, and we had a mixed design, so some users started with the pad, others started with the stylus, and these results are from the experts group, but similar results were from the other medical groups. And as you can see, the natural interaction and more fitting hardware was significantly rated in favor of the pad against the stylus. However, there was also some neutral or not so good rating that some people had some problems interacting with the pad. And then we also asked them to further elaborate, and they explained that they wanted to hold the pad at a different angle. And so this brings me to the next slide. So we had several observations and comments. So many of the medical staff were first intimidated by this haptic input devices. They had never seen such devices before and were afraid to use them, but after a very short time they got used to it and were able to control the simulator very intuitively. And what was also very interesting to see that the medical staff treated the simulator like a real patient, so they got really immersed in the simulation, and you could see how they were very carefully conducting the procedure, and they really heavily relied on the palpation before they started to insert the needle. So this was really important and good to see. And furthermore, there was no complaints about the hardware setup. This was not co-located. So sometimes the system is also co-located, but the visuals and haptics are in the same place, which can be achieved with a mirror system. And some of the lessons learned were that we should offer variations of the pad for different finger postures and different sizes and so on. And we should also use some stronger haptic devices, and we should also somehow try to hide or cover up the devices so that people are not so quickly intimidated by the devices. So this brings me to the end of this first part of the talk, and I want to quickly summarize. So I've presented a palpation interaction approach, and there we have a tissue dragging algorithm and force rendering and this hardware extension. And you can also see the looping demo video on the right side once more. And furthermore, we've conducted an extensive medical user study, which hinted that we've created a plausible simulation, and also showed in some cases differences between experts and novices. And some of the future work will be to improve the haptic devices or use other devices and increase simulation fidelity with higher resolution meshes and more advanced algorithms, and also the medical staff wants to have more content so that they can perform different kind of procedures in different body regions. And of course, it would be also good to conduct more studies. So one idea would be to have a control group that undergoes training without a simulator, and another group that's having training supplemented by a simulator, and then compare the performance of both groups, which one performs better. So this ends the first part of the talk, and now I come to the bonus slides. So I took the title of this webinar, Simulations that Can Save Lives, and for me this is not really a statement but more a question. Can those kind of simulators really save lives? And for me, the short answer is yes. This kind of simulators can be used for training and rehearsal, and thereby they can minimize the errors and thus indirectly save lives. However, I think there's also still some obstacles and problems. So there's simulation challenges and further research required, and also very important is the acceptance of a simulator. So that's why this user studies are very important to convince the medical community that the simulator is valid and also useful. And I also see that the development of such simulators is very fragmented. So there's many research groups that are doing research on medical simulators, but in my opinion, there could be more collaboration in between to further advance the development. And probably also one of the limiting factors for now is the high initial costs. So the systems still need to be developed, and so it will take some time until they amortize in their value. And so I want to compare medical simulation to aviation, and for this, first talk about simulators in aviation. So pilot has to do many hours in a simulator before he takes the first time off with a real plane. And also, when the pilot has his license, he still needs to conduct regular training sessions in order to keep his license. And these simulators for aviation have been developed for almost a century now. And computer simulation has been used in aviation since the early 60s. So by now it's already very advanced. And on the other side, in medicine, there's many challenges. So there's many different procedures which cannot be all covered by one simulator, obviously. And also the human physiology and anatomy is very complex and in some parts not really understood yet. So that also complicates simulation. And there's no standards and regulations for simulators yet. So that would be something that would be helpful. And also to complicate things further, there's many variations of how a procedure is conducted. So between hospitals and even within one department, between different surgeons, there's different ways to perform a procedure. And this is something which a simulator should either also cover or the procedure should be more standardized. So now I want to give a short overview of what kind of medical procedures are covered in simulation. And one example, that's the most popular probably, is minimal invasive surgery. So there's many research and also some commercial simulators available that allow the user to train minimal invasive surgery procedures. And then there's also systems for dentistry with haptic drilling, for example, that are getting more and more popular. There's a few approaches with needle insertion, and there's even fewer approaches with palpation interaction. And but I also think that the palpation interaction is just one interaction metaphor which should be supported by many kinds of simulators. And so there's still many procedures that are still missing. And on the next slide, I want to give a rough assessment of medical simulation. So I think there's much ongoing research and development in both academia and industry. And this is also a highly interdisciplinary, exciting field. So there's medicine, computer science, biomechanics, continuum mechanics, and many other disciplines which I didn't list in here. And from the software point of view, I think that, for example, the visual realism can benefit from advances in the gaming industry, for example, and also open source should be used more often to share results and not to start from the beginning again, but to further accelerate the development. And from a hardware point of view, simulators should be developed for different platforms. So, for example, nowadays smartphones and tablets are becoming more and more popular, but I think simulators should support all kinds of platforms. So some stages of training could be conducted by a doctor at home on a tablet, and other stages of the training should be conducted on a dedicated immersive system with haptic devices. So speaking of haptic devices, those devices are still very expensive and in my opinion far from finished. So for in order to support all kinds of procedures, we need more devices to choose from. And lastly, data sets are also very important and often underestimated. So there's medical imaging to acquire anatomical data sets, but then there's also research on image segmentation and so on. And if a data set has been segmented, then we still need to prepare it for the simulation so that the simulation can be conducted in real time. These are all challenges that require all kinds of specific knowledge. And on the next slide, I just want to show two examples of medical simulation open source projects. So one is SOFA framework, which is developed mainly by some in-real institutes, and it's a framework that's based on C++ and that is intended specifically for medical simulation, and it contains many different algorithms, for example, for with finite element-based approaches for soft tissue simulation, different ways of collision detection, and many more things. And you should just check out their webpage and have a look at this software if you're interested. And the other one is H3D API, which is developed by SenseGraphics, the company that I work for now. And this toolkit is based on the X3D standard, and it supports many different haptics devices. And it allows you to do rapid prototyping and also development by using this X3D format, and you can do scripting with Python or implement procedures in C++. And it has many interfaces to different APIs, and just as an example here I mentioned two physics engines. So one is a bullet physics engine, and the other one is SOFA now, which will be also integrated into H3D. And this H3D is used both in commercial simulators, and it's also used by universities in research projects. So have a look at the website, and just to show you one example of what is possible with H3D. So this is a screenshot of minimal invasive surgery simulation that is implemented in H3D. And you can see two robotic arms here, and this is the liver, which is lifted up, and gallbladder is getting approached to get cut out and removed. One other important aspect, which I mentioned before, is standardization. And for this, I just have this quick slide on Web3D. So the Web3D consortium is working on ISO specifications for 3D and 4D content, and has created, for example, X3D and so on. And in this consortium is a medical working group where I'm also a member of. And some of the goals of this group is medical visualization and data exchange. And one example is a volume rendering component, which is now being added to the X3D ISO specifications. And there's also links between the medical imaging format DICOM and X3D, which is being established by this working group. And our future work is to establish components for soft body physics and for haptic rendering to allow an exchange and further accelerate the development of medical simulators. So have a look at the website if you want. And yeah, to wrap up this bonus slides, so I asked the question, can those simulators save lives? And I already said yes, they can, but there's still many challenges. And just to give some motivations what to do, I think it's very important to communicate with the medical experts and students, because they are the ones that are going to use this simulators. So this is very important. And also collaborate with other disciplines. Don't try to solve everything on your own. And use more open source tools. Try to establish standards to ease collaboration and get more funding. And so push the envelope and continue the development and try to get simulators into medical curriculums. So yeah, this ends my presentation, and I just want to thank all the people that have been involved in this work, my PhD advisor, boss, and co-workers, project partners, participants of user studies, reviewers, and the whole community. Thank you very much. This is it from me. Now you can ask the question.
Thank you, Sebastian. We have a couple questions that have been submitted, and then we'll start off with this one. Why was collocation not a factor? Was it due to the irrelevance of visual feedback?
I think the collocation wasn't that big of a problem because we were using this hand avatars, and yeah, probably also because we just had a minor, we tried to minimize the offset between the haptic device and the visual output.
Great, thank you. The next question is the source code for this project available?
Well, I would have to talk with my previous supervisor, but for now it's not available, but parts of it will go into open source projects definitely. So not available right now, but parts of it will become available definitely.
Great. Next question. What API do you use with the Phantom Omni device?
Okay, so it was using Open Haptics, which is the API that's provided by the company that produces Omni device. But now I'm also using H3D, which supports more devices. Yeah.
Okay, for the next question, you presented some nice survey results. Do you have objective measurement data specifically from the experiments regarding accuracy, repeatability, etc.?
So during this user study, we also recorded the time that it took the people to the task completion time, and we also recorded the trajectories, but it was not a repeated measures design. So we had some other user studies and we did some repeated measures, but this was mostly to get their subjective feedback first, and and do other objective measurements later. And it's also difficult to measure palpation objectively.
Okay, for the next question, what SDK have been used for this project?
So it was different kinds of SDKs. Also in the paper it is described in more detail. I used a Vista Virtual Reality Toolkit, I used a SOFA framework, I used Open Haptics, I used a Bullet for collision detection.
Okay, for the next question, did you take into account the properties of the blood vessels or only the soft tissues for muscles, skin, etc. in the pulse haptic simulations?
Well, so the blood vessels are modeled by this pulse points, and but they are not used for the soft tissue simulation. So we don't make the tissue any stiffer if there's a high blood pressure or low blood pressure.
Okay, next question. What specific benefits could be gained by looking at computer game software?
Well, I think computer games are very stylized and use very much shaders and the way they present the content, and so there's a lot that could be used to make a simulator nicer looking. So this is one thing that doctors will also complain about. If it's too abstract, they say, I cannot really relate to this. This doesn't look like the real procedure. And yeah, also the modeling the content and so on. That's very important.
Thank you. Next question. Can you use this device in laparoscopic surgery?
You mean this haptic device, I guess? I think, yeah, it could be used for laparoscopic surgery.
Okay. Next question. Why do you conclude that stronger haptic devices are necessary? What kind of forces were you expecting to render?
Well, so one thing that we encountered during the user study was that one of our test subjects broke one of his haptic devices. So some of the doctors, when they cannot find the pulse, they increase the pressure until they find the artery. And in this case, I didn't say stop quickly enough, and then the device was broken. So yeah, that was just that some people are exerting more than 3 newtons, and this one had a very strong grip, and well, she just broke the device.
Great. Next question. Did you make a mathematical model to simulate all the properties from all the soft tissues and blood? If yes, are these models available?
For collision detection with the needle, we used all these different soft tissue layers, like the muscles, the blood vessels, bones, and so on. But for the soft tissue simulation, we simplified it, because otherwise it wouldn't have been possible to conduct the simulation in real time. But at least we fixed behavior points that were inside of bones so that they couldn't move, and so there was a coarse simulation of the different tissue types. But this is something for future work, definitely, to simulate each tissue individually.
Thank you. Next question. While performing actual surgeries, doctors get to feel the human body parts. Have you tried to develop the same in your project?
You mean if this could be extended to other body parts? Or what was the question again? Can you read the question once more?
Yes.
think I did.
The question again is, while performing an actual surgery, doctors get to feel the human body parts. Have you tried to develop the same in your project?
Well, we've simulated the hip region, but for other procedures, also other regions could be simulated. So it's just a matter of creating 3D models of those and changing soft tissue values and so on. So yeah, it should be possible.
Great. Thank you. I think that concludes all of our questions for today's presentation. I would just like to first of all thank you to Dr. Sebastian Ullrich for this very informative presentation. I'd also like to thank all the attendees for taking the time to view and listen to the webinar and submitting the questions. Also, as far as the slides and a recording of this presentation, they will be available after. All those who have registered will receive a link for those. And on behalf of the IEEE Computer Society, thank you again for attending and have a great day.
Thank you also from my side. for attending and for the questions.